Hello everybody, today I'm going to demo the PID controllers which are part of the home controller platform. Before I jump into the demo, I'm going to just talk a little bit more about what is the home controller project and how it was architected. So our group wanted to develop a platform that would be able to connect to any IoT device in your house. And not only that, this platform would be smart enough to gather input from the users, and this input is basically command requests, and balance those command requests to find the most optimal state for the IoT devices. An example of that would be light bulb control. So we're actually in this demo, we're going to be controlling the Philips Hue, which is an IoT device that control light bulbs in your house. So let's say 3 users want to raise the brightness of a room, and 2 other users want to lower the brightness of a room. The responsibility of the system is to try to balance it out and find the most optimal case, and for that we're using a PID controller. This system is also really is capable of many types of inputs. So we're not only accepting web GUI inputs, so we have a web interface, but we also have a voice command application where the users can trigger commands, and we also enable users to trigger commands using their brainwaves, using a brain-computer interface, a BCI interface. So there's many ways users can input commands, and our system is going to be responsible for balancing those commands and finding the most optimal case. So yeah, in the left of this diagram, you guys can see the users triggering web commands, audio commands, voice commands in this case, and also brain-computer interface commands. I'm not going to just detail much about the command triggering on the left side. For those, I'm gonna leave videos in the video description explaining each type of command triggering input. So if you're interested to see the web interface, there's going to be a video for that, voice commands as well, and brain-computer interface as well. I'm going to jump more to the actual architecture of the system. So whenever the commands are dispatched, those are dispatched to a GraphQL API. This GraphQL API is responsible for authenticating users and also registering users, dispatching commands and also registering commands. And it also contains our PID controller, which is going to balance out all the inputs from the users and trigger and communicate directly with the IoT devices. So this is our central hub here. It's going to manage users and save those in a database, commands and save those in a database as well. And finally, it will get all those commands in real time, balance, and communicate directly with the Philips Hue bridge. Besides that, we have a PID controller load balancer. So this is the same load balancer used in assignment 2. It's basically a Python load balance that will be creating new instance of the GraphQL API, and also it will generate new instances of the EEG API. I'm going to talk about this other API in a second, but let's just focus here for a minute. So this PID controller is responsible for basically doing load balancing. So we do have a PID controller to balance commands and a PID controller to load balance and also create new containers for the GraphQL API and the EEG API. So besides that, we have a really specific use case that we also covered. For the brain-computer interface, we dispatch those commands to the GraphQL API, and those are sent directly to a Kafka queue. This queue basically it will pile a bunch of messages, and those messages will be consumed by an EEG API. Basically, this API will consume those messages, will generate some classifiers. In our case here, it's generating multi-layer perceptron, SVM, and random forest. Again, I'm not going to go much in detail in this part to this part as well, because it's not related to the actual PID part, to the actual PID project. But we're using Kafka here. We're using the queue to dispatch those messages asynchronously, and we are also consuming the queue on the other side and generating our classifiers in real time. As soon as we generate our classifiers and we classify the brainwaves that are coming from the user, those are pushed back to the queue, and then the queue returns those values to the GraphQL API, which communicates back to the user. So for the iPhone, for the mobile application that we have, the iPhone application, all the brainwaves that is coming from the Near Sky Mindwave mobile headset is being sent directly to the server, then to the queue. Finally, the queue it's consumed by this application, and this application pushes back the classification for those brainwaves. So this is basically the architecture of the system. Next, I will review the first PID, which is the PID that controls command input, and then I'll review the load balancer, and finally the queue and how it works and how it's managing the message flow.
In order to trigger commands, we're going to use the web interface for now. First thing we need to do is basically create an account. So we're going to click here on create account. I'm going to specify a name. Right now I'm going to just call it test. And I'm going to just use test. And the password is going to be 1234. I'm going to create this account. As soon as I create it, then I'm sent to this page here. I'm redirected to this page where I can add and manage commands. So I'm going to add a new command here. And as I mentioned in the presentation, we have 3 types of commands. So we have voice commands, BCI, the brain control interface commands, and also the GUI commands. So we're going to just select GUI for now. And we're going to specify a name for this command. So I'm going to just call it on. And this command will just turn the light on. I'm going to create a new command here, add command. The other one's going to be called down. And we're going to just turn the light down. And I'm going to create 2 other commands. One I'm going to call brightness up. So I can actually copy this here. And this command would just increment 200 to the brightness. And brightness down will decrement it. Here we go. Perfect. So we can save that, and as soon as we save, we get redirected to another page where we're able to trigger the commands.
So here we have access to the platform live. The lights are connected over there, so we can actually trigger commands. So I'm going to just calling the down command and click OK, and lights go down. If I click on, lights go on. And yeah, obviously I can also play with brightness. So if I increment brightness, it will change. Let me point directly to the light, maybe a little bit easier to see. So I'm going to decrement some brightness right now, and now I'm going to increment the brightness. So okay, so the next step is going to be showing the PID control in action. Okay, so let's test our PID right now. Just some quick adjustments on brightness up. I changed it to 15, and brightness down I changed it to -15, just to be a little bit more balanced. In this platform we have a PID section where we can set our KP, KI, KD. We can even deactivate or activate the PID controller. We also have a K variable here that the user can manipulate. Set point is going to be the values for brightness goes from 0 to 254. So our set point is going to be 150 here, which is kind of in the middle. The time interval, those are all the commands emitted in the last 30 seconds, in the past 30 seconds. We can change this as we want as well. So yeah, we're going to save this right now. We can go to send command here. And as soon as I start sending commands here, I should be able to see those over here. So we have we have everything here. So we have our T here, our error rate is here, our set point is here, our previous utilization. Also I got the output proportion, the integral and the derivative. And then we spit a balance command value. So let's say the user's trying to put +15, but we already have a process variable of 201. Like here, we have a variable that is already over the set point, over the threshold. Then we're going to try to balance it out. So right now the room is pretty dark. We have this set up here. I'm going to trigger increment up and up again. And as you can see, the process variable is increasing 15 by 15 to the point that it's 149 now, 164, and then it locks 171, 158. If I try to decrease it, then 131, but then it goes back to 146. So it's floating around the set point as established. Okay, before jumping to the PID load balancer, just a quick explanation. We divided our infrastructure in two files here. One Docker Compose apps file and the other one is Docker Compose Kafka. The apps file contains all our services, so databases, so GraphQL database, GraphQL API, EG database, EG Brainwave API. We also have the web interface, the web client, and finally container visualizer. We're going to use this guy here to visualize our containers in real time between virtual machines. Finally, we have the Docker Compose Kafka, where we have all related services for Kafka. So Zookeeper, the key store, the key store service. We also have the broker itself, and we also have an interface, topics UI. So we're going to be able to see our queues and topics, our topics and partitions in real time. But anyway, so we divided the project into those two Docker files. Besides that, if we want to deploy the stack, we just do docker stack deploy, and we feed those two files to it, and we call it home controller. That's basically it. In terms of the scaler that we're using, in terms of the actual PID, it's the same it's the same one from assignment 2. The only difference that we're passing some certification files here, some certificates actually. We're feeding the two IPs here for the master and the node, same thing. And over here, the only change that we've made is that now we have a service thread function, and we can just call this function with a service name. So in this case, I could call that function passing home controller GraphQL API, and that will generate a thread. This thread will start executing and monitoring the service. So we could call many threads in different services and run those in parallel. For the purpose of this demo, I'm going to just run one thread on the home controller GraphQL API, and I'm going to just call JMeter in a second with some sample requests to see how it handles it. We're now going to run our PID balancer. Great, so it asks for an upper threshold. We're going to put 60, a lower of 30, KP of 0.1, KI of 0.1, and KD of 0.2. The interval is going to be 5 seconds. And finally, we can see it running. So we can see all the values. The CPU average right now is 0 because we're not calling the API in any shape or form. So the next step is going to be, we also can see like the services by just doing servers ls. Right now we just have one replica. And we have the visualizer here where we can see the containers. So we're going to just get JMeter. I'm going to have 100 requests. We have authenticated requests here. That's going to basically get some user information. I'm going to run it right now. Okay, it's running. And we should see a little bit of a spike. Here we go. So the spike happened. If we go back here, we're going to scale up, so we're creating new containers here, as you can see. So we still have CPU is still up, so we're going to create a little bit more containers there. Yeah, we're creating more and more containers. Finally, we have 8 replicas right now. CPU is just really it's really high. And also it's good to remember that the actual scaling does generate some overhead. So anyways, but now we're getting lower CPU average here. We have 11 replicas running. And now our CPU usage went all the way down, and we're scaling down massively as well. So now we're going down, and we can see that here in real time some blocks will disappear. Those are represented to be the containers. So yeah, as the scaling down happens, they will disappear from the first VM and also the second VM here. And now we have 9 containers, 5, and yep, and it's going down to the point that again, we already have a CPU usage that is 100% fine. So yeah, here we go. We are pretty much back to the initial state of 1 container per service. Bear in mind that we have 10 services running, so yes, there is overhead for the scaling process as well. So even with a really refined PID, we still have a little bit of overhead in terms of CPU because of the actual VM CPU consumption to scale up and create new containers. But anyways, that's pretty much the PID for the balancer. Now we're going to jump to the queue explanation and the queue demo. So for this part of the demo, we're going to create 2 separate accounts. First one is going to be daniel@gmail.com, and inside this account we're going to create some mind states. So open eyes and closed eyes. I'm going to save that, log off, and create a second account. We'll call Daniel2, and this account will also have some states. Open eyes, closed eyes, and we also gonna set up a BCI command. So BCI, and we're gonna set open eyes whenever the eyes are open, lights are up. Whenever the eyes are closed, then the lights are gonna be off. So now we have the 2. Okay, so now we have our iOS application open. We're going to log in with the first account. We have our headset turned on. It's going to sync with the Bluetooth in the phone. So we have the waves right now. The blue one represents meditation, red is attention, and yellow is blinking. Right now, the idea here is that we're going to classify a mind state, and that's important to generate the classifiers, and those will be used to send information through the queue as well. So I'm going to do open eyes for now, and I'm going to do some classification with open eyes. So I'm going to just keep my eyes open, and as the system records my mind waves, and I'm gonna just stop that right now, and I'm gonna do closed eyes, and then the system is gonna record my mind waves as my eyes are closed. So I'm gonna have different mind waves between those 2 states of mind. Like you're actually able to code any other state you want. That's the idea of the system, but for the demo we're just coding those 2, and there we got it. Okay, so now we have 2 states of mind. In the bottom here, you can notice that we have random forest, SMO, ML, perceptron. Those are the classifiers that we have, and those will be generated. Oh, okay. So if the data that we just collected that went through the Kafka queue got consumed by another API, and the other API created the models for this user, the classifiers. And with the classifiers in hand, whenever we push new EEG data to the Kafka queue, it consumes it, and it also classifies it and pushes it back. So we're going to see that in a little bit more detail right now. But before that, I'm going to just click back. I'm going to log in with the second account, which is over here, Daniel2. Again, this account I also created 2 mind states, open eyes and closed eyes. I'm gonna start classifying with open eyes first. So just gonna collect a little bit of data as my eyes are open, and that should be fine. We're not here to create a strong classifier right now. And closed eyes. So we're just going to collect a little bit of data right now, and that should be fine as well. And same thing, so classifiers are being generated. Now that we have 2 classes, we're able to generate a classifier. So the GraphQL API pushes the data to Kafka, to the Kafka queue. The queue gets consumed by a Java application, which is running Weka, and finally that data is used to generate classifiers. Okay, so the classifiers are being generated. We're not gonna wait for that, but still, now we're gonna jump into to the actual Kafka visualizer, the interface, so we can see which types of informations are we which types of information are we trafficking in the Kafka queue. To the desktop, and we're gonna take a look at that data. Right now, just a quick recap. GraphQL is sending raw EEG data to the Kafka queue, more specific to partition 0 of this queue, and to a topic called EEG. So we have a single topic for this application, which is called EEG, and partition 0 is going to carry all the information coming from GraphQL directly to this, all the raw EEG information, and this partition 0 from the EEG topic will be consumed by our EEG API. As soon as it consumes it, it's going to store the data into this database, create a bunch of classifiers, and start classifying the data and pushing it back. But the gist is, whenever it pushes it back in different partitions. So for example, for a user with ID 1, it's going to push the data back to partition 1. For a user with ID 2, that's going to be partition 2. So if we take a look, we've come back here to the interface. So this is one of the services that I've included in the Docker Compose. We've included in the Docker Compose. Right, it's just called EEG, so we can click over here, and it's going to load it for us. And right now we have 7 partitions. So the first one is the one that is getting all the raw data, and the other ones are related to users. Right now, whenever partitions are being created dynamically in the application, and the reason why we have 6, even though we have only 2 users, is that whenever we need to expand the number of partitions, I'm not increasing by 1, but I'm actually increasing by 5. So whenever I need to create partition 1, I also created like 6 extra partitions, because it's an expensive action to do actually. If we go back to the data, we can also notice that we're going to have 2 types of data here. So we're going to see like partition 3, that's from the second user. But we can, if we click 65 here, that's like one of the first first messages that we send to the queue. That's on partition 0, so you can see the message is quite raw. Is the EEG data, like we have time, we have the theta, low alpha, high alpha, and the user associated to the data. So in this case here, user 2. But as we move here, as we paginate, we are not only going to see raw data, but eventually we're going to be able to see classified data, which means that this data was classified. Okay, so here we go. So this means that the user, the phone basically dispatched a message to GraphQL. GraphQL sent the message to this guy. This guy generated asynchronously a bunch of classifiers, and now we're pushing it back. All the classification is being pushed back to the queue, and that's an example of it. So right here we have SMO, random forest, and multilayer perceptron. This is a message being pushed back on partition 2, which means that's associated with user number 2, with user with the ID number 2. And yeah, so we have a bunch of messages here. It's non-stop. And yeah, that's mostly what the queue is. That's how we expanding partitions. We've made a Kafka service. This service basically connects to Kafka and generates a client, a consumer, and a producer. So that's how we're manipulating it right now. We're getting some environment variables from Docker, and that's how we're doing it right now. On the Java side, it's pretty similar. We have a Kafka thread, which is executed as soon as the API starts. And here we have a consumer, a producer as well, same thing. The only difference is as we consume the data, we're gonna check if we need to create a new partition, as I mentioned. So the partitions grows as with the number of user continuously with the number of user IDs. As the user IDs grows, but the partitions will do the same. And here we actually classify the data, and we run a producer, and the producer pushes the data back, the classification back, and that's basically how it works.